function of theta and phi becomes this YL-ML function, okay? And a new quantum number arises from the boundary conditions. We call it the angular quantum number L, which should be familiar to you, and that takes on values 0, 1, 2, etc. What also becomes really cool in this solution is trying to solve these things together, right? Because we have the ML term right here, which comes from the phi solution. We get the L from the theta solution. However, what becomes difficult is the L and the ML have to be connected to each other. And it becomes the following. So ML takes on two L plus 1 values. That is L, L minus 1, all the way down to minus L. So where do I get this 2L plus 1 values? Well, for example, if L is equal to 1, then ML can be 1, 0, or -1, right? So where do I get the 2L plus 1 values? Well, remember, if L was 1, 2 times 1 plus 1 equals 3. That was 3 values of ML. So we're going to see this 2L plus 1 come up. Okay. So what else do we get from solving the spherical harmonic particle on a sphere? Well, we get the energy solution, and we actually get the energy solution in terms of quantum number L, which is cool. It becomes L times L plus 1 times h bar over 2i. So this h bar over 2i should be familiar because recall when we did the particle on a ring, let me find that solution for energy. Yes, look, when we did particle on a ring, we still got that h bar squared divided by 2i, however, it was times ml squared. So we're really seeing the connection between ml and L from solving this model. At least you'll have to take my word on it because I'm not making you finish doing this solution. Okay, a couple other things to point out before I wrap up this lecture. These spherical harmonics, much like the Hermite polynomials, really start to blow up when you add in their quantum number dependence. So for example, when you have L equal to 0, and then of course ML, the only value you can take is 0 because, right, 2 times 0 plus 1 is just 1. So when L is equal to 0, ML has to be equal to 0. Well, my YLML, my spherical harmonic function, becomes the square root of 1 over 4 pi, okay? With no theta or phi dependence, which is kind of cool. We'll see the manifestation of that in a moment. When L is equal to 1, then ML can be 0, plus 1, or minus 1. And now what we should notice is the plus 1, minus 1 states have the same function, although they're just different in sign. So for example, when ML is plus 1, so the notation of this is kind of weird. So when ML is plus 1, the function starts as negative square root of 3 over a pi, sine of theta, e to the positive I phi. When ML is equal to -1, the function becomes positive square root of 3 over a pi, sine of theta, e to the negative I phi. Okay, so keep that in mind when you're noting these functions. And you'll notice definitely as we get to bigger L and ML values, the spherical harmonic functions become a lot more complicated. So it would have taken us days and days and days to solve this thing, okay? So that's why we're not going to do it. But carrying along, okay? The normalized particle on a sphere Schrodinger equation becomes the spherical harmonic functions. The spherical harmonic functions give rise to new quantum number dependencies, that is L, angular momentum, or angular quantum number, and ML, magnetic quantum number, and we can see the dependence of them. And then now what we also see is some other unusual integral properties that I don't think are as important but worthwhile to note. And I'm not going to review those in great detail, but here we can see the spherical harmonics are orthogonal and normalized in the following sense. Okay, So so this is the normalized equation, and this is the orthogonal equation. And this is kind of a weird orthogonal equation because you notice here that it's using 3 spherical harmonic functions, and that's to set up what we call the vector model, and I'm going to be going that in the 3rd lecture of this material. So I'm not as concerned with you knowing these integral properties, but I just wanted to present them, that the spherical harmonics do have these integral properties, okay? Another thing that we can start to look at is when we plot these spherical harmonic equations, which we're going to do. You're going to do that in your Math 6 assignment. They start to take on some familiar shapes. So let's look back to this L equals 0 and ML equals 0. Okay? So in the solution for the YML, there's no theta or phi dependence. And so what that means is the y0, 0, so I would call this solution here the y0, 0, because L is 0 and ML is 0. Look, it's just a sphere, like an s orbital, right? Awesome, cool, because it is an s orbital, but you don't know that yet. We don't know that yet. We'll get there. So what about these functions? Well, right here, so this is also really cool. So this one is the y10, and I want you to stare at that thing for a minute and think about what that looks like. If you're saying a p orbital, then you are exactly correct. And in fact, it is specifically a pz orbital. And this is going to come full circle with our Heisenberg uncertainty principle, why that one is pz. So now what's going on with this donut-looking shape? So this one is the y1 plus or minus 1. So because the plus, so remember, I talked about those ML states, they're doubly degenerate, okay? So why does it look like a donut? Well, now what I want you to imagine, take this p orbital, okay? Rotate it 90 degrees, and then now take that same p orbital shape and smear it all the way around your xy plane. And that's the shape that you would have. And so the reason why that doesn't resolve perfectly into a px and a py is because, as we shall see, there is an uncertainty relationship associated with those x and y dimensions. We see the same thing with L is equal to 2. So the y2, 0 is right there, and it is a perfect dz squared orbital. That's what we call that thing. So then now the y2 plus minus 1 and the y2 plus minus 2, they kind of look like d orbitals, but not quite, because we have to deal with Heisenberg. And then now similarly also the y3, 0 looks exactly like an fz orbital. The other orbitals don't quite look like what they're supposed to look like because we haven't dealt with Heisenberg yet, all right? And plus we also haven't dealt with what happens when we change the radius. So what we have in these pictures right here, these regions are showing you the angular nodes. So we've talked about nodes in the translational model. And as it turns out, we can call those radial nodes because those nodes appeared on the radius axis. And we'll hit those again soon, okay? The angular nodes are a little bit more hard, or they're a little bit more difficult to visualize. So these angular nodes are represented by shaded regions given right here. So the L00 doesn't have any angular nodes. The L10 has angular nodes, and to be determined how many there are. But I just wanted to start pointing out that we can start to kind of get a sense of what's happening, foreshadowing, talking about our atomic orbitals to come, okay? And so let's see here. So that's a good place to stop. And in the last video of this content, I hope it'll be the last video of this content, we'll continue on with this model and build up what we call space quantization and the vector model. Okay? So